Okay, section 17.2, buffer solutions. So we've now gotten to an very important section, particularly in biology and biochemistry, buffer solutions. So I'm going to define a buffer as a mixture, a solution that has a weak acid and its conjugate base. To be complete, we'll also say that it can also be a solution with a weak base and its conjugate acid. Okay, so let me show you a couple of examples. So an example would be HF. That's a weak acid. Back from chapter 16, the list of weak acids. HF is one of them. The conjugate base would be the fluoride ion. So if you have HF, hydrofluoric acid, in a solution with the fluoride ion, you would have a buffer. Likewise, if you had a weak base, ammonia. This is from the list of weak bases in chapter 16. NH3 is ammonia. And its conjugate acid, NH4+, you would also have a buffer. So weak acid, conjugate base, weak base, conjugate acid. If you have these two or these two, those two combinations, you have what's called a buffer. Okay? Now I do want to point out that generally the base that we're talking about here, either the weak base or the conjugate base, is often in the form of a salt. So for example, fluoride would be added to the solution by adding sodium fluoride, or perhaps potassium fluoride. These salts are very soluble in water. Sodium and potassium are the conjugate acids of very strong bases, so they have no effect on acidity. So sodium fluoride becomes sodium and fluoride. So there's your conjugate base there. Just like potassium fluoride becomes potassium and fluoride. All right? Okay, so we've got this idea of what a buffer is. Now, what's the significance of a buffer? Buffer solutions resist changes in acidity. And for shorthand, we'll say pH. It's easier to say pH than it is acidity. They're a measure of the same thing, essentially. So a buffer solution resists changes in acidity. This is very useful in biology. Cells can regulate their pH if they're exposed to acids or bases. The oceans of the earth are buffered. The pH of the oceans changes very, very slowly, even with enormous additions of acids or bases to the oceans. So it's a very useful phenomenon. It's based on the common ion effect, which we talked about in section 17.1. So let me show you an example. And the example we're going to use is we're going to take 1 molar of acetic acid. And acetic acid is a weak acid, so it has a Ka of 1.8 times 10 to the minus 5. Where did I get that value? That's back in chapter 16, right? The weak acids. You don't have to memorize those values, but you need to be able to look them up. In that same solution, let's put in sodium acetate at the same concentration just to keep things simple. Sodium acetate. Don't have to worry about the Kb there. We're not going to use the Kb for that acetate ion in this calculation. Okay? And then let's mix them together and make the volume 1 liter. So I'm picking numbers just to make things nice and easy. Now, let's go ahead and calculate the pH of this mixture. Okay? How do we do that? It's a weak acid problem. So, acetic acid dissolved in water reacts with the water. Weak acid reacts with water. It's weak, so it's reversible. So we get the hydronium ion, and we get the acetate ion. Okay? So, now let's do the following situation. We know that the concentration of the acetic acid is 1 molar. Water is a liquid, so we don't need to worry about that. Hydronium is 0 initially. And the acetate is not 0, it's 1. However, because the hydronium ion is 0, Q is still 0, right? 0 times 1 divided by 1 is still 0. So the reaction still goes to the right, even though the acetate is not 0. So we fill in the appropriate values into the ice table. Okay, now let's take a look at what happens to the calculation. Ka is 1.8 times 10 to the minus 5. That is equal to x times 1.0 plus x divided by 1.0 minus x. Okay? Now, because Ka is very small, we can assume that x is going to be very small, at least compared to 1. So we can approximate this as x. 1 plus x becomes 1, and 1 minus x becomes 1. Right? X is small compared to 1. The 1's divide out, and you just get x. Now, x is the concentration of hydronium, so the pH is just negative log of x. Okay? Now, that's equal to, let's take a look. X is equal to 1.8 times 10 to the minus 5. So minus log of 1.8 times 10 to the minus 5. If you run that through your calculator, you get 4.74. Okay? So this particular solution results in a pH that's 4.74. Notice that it's still acidic, but it's not as acidic as it would be if it were just a weak acid. It's not basic like it would be if it was just a weak base. Okay? Now, let's get to the significance of how a buffer functions. What I'm going to do is I'm going to run through this same solution. I'm going to add a strong acid to it. Okay? So here's what we have. I'm going to rewrite that we have CH3 COOH, aqueous, and water, liquid. And now we have H3O plus and CH3COO minus aqueous. And initially, we know what our values are, right? Initially, this one is 1 minus x, which is just 1, right? So it really hasn't changed any. Water's a liquid, you don't need to worry about that. Hydronium is x, right? So that's 1.8 times 10 to the minus 5. And then the acetate is 1 plus x, 1 plus 1.8 times 10 to the minus 5. Well, that's just still 1, right? 1.8 times 10 to the minus 5 is so small. There we go. Now, what we're going to do in this particular problem, so let me make a little more room over here, is we're going to add 0.10 moles of HCl. Okay? And what's going to happen when we do that? When we add 0.10 moles of HCl, this is an acid, right? HCl is an acid. And you ask yourself, what does an acid do? What does it react with? Does it react with other acids? Do acids react with acids? Not really. Acids usually don't react with acids. There are some exceptions to that. It can happen. But generally, acids react with bases. So if we look at our 4 materials that are in this balanced equation, which of those 4 is a base? It's not acetic acid. That's not an acid. Water can be an acid or a base, right? It's amphoteric. Hydronium, well, it's hard to think of that as a base. Acetate, however, is a base. It's a weak base. It's a weak conjugate base, right? So what's going to happen is the HCl is going to react with the acetate. So what we're going to do is we're going to write a little reaction here. We're going to take 0.10 moles of HCl and we're going to react it with the acetate. Okay? I'm picking acetate out of those 4 in the equation up at the top because that is the strongest base in the equation. The acid HCl is going to react with the strongest base of those in that mixture. It's a 1-to-1 relationship. Now, how many moles of acetate do we have? Let's come back to the original. We said that the buffer had a volume of 1 liter, and the concentration of the acetate is 1 molar. So how many moles is that? Let's come back. Molarity equals moles over liters, right? So that means moles is molarity times liters. So that would be 1 mole per liter, 1 molar, times 1 liter. Well, that's 1 mole. Okay, so we know we have a mole. Now the next step is to figure out what's going to get. What do you get for products? Again, think of it as Bronsted-Lowry chemistry. We don't need to worry about Lewis acid-based chemistry here. Do it as Bronsted-Lowry. Acid, base. Acid donates the H plus to the base. So you get chloride, and then you get acetic acid. Okay? Now, over here, is this initially 0? Come back over here. That's not 0 there, is it? It's 1.0 molar, and just like with the acetate, the volume is 1 liter, so 1 times 1 is 1 mole. So this is not 0, it's 1 mole, right? So this is our buffer is now reacting with the HCl. It's the conjugate base that's reacting with the HCl. So now, what's going to happen? Well, it's not really an equilibrium reaction here. This is just a simple go to completion reaction. It's a limiting reactant problem, actually. The HCl is 1/10 of a mole. The acetate is 1 mole. So what you do in this case is you subtract the smaller of the 2, the limiting reactant. Okay? Oops, look what I just did. I made a little mistake there. The limiting reactant is the HCl, 0.10 moles. Okay? And then this is going to go up by 0.10 moles. So now, once the reaction is complete, again, it's not really equilibrium, 0.1 minus 0.1 is 0 moles. So there's no HCl. It's been reacted completely. But now the acetate has gone down to 0.9 moles, and the acetic acid has gone up to 1.1 moles. Okay, so these are our final concentrations now. So now if we come back to our expression for equilibrium for the acetic acid, the Ka for acetic acid is the concentration of hydronium times the concentration of acetate divided by the concentration of acetic acid. Okay? Well, we know the Ka is 1.8 times 10 to the minus 5. We've got that value. But do we know any of these values here? We don't know the hydronium. We know what the original hydronium was. It was 1.8 times 10 to the minus 5, but it might be different now. So let's figure out if it's changed. The number of moles of acetate is 0.9, but the volume is a liter, so the molarity is 0.9 over 1, so that's 0.9 molar. And the same goes for the acetic acid. It's 1.1 moles, but the volume is a liter, so that's 1.1 molar. So now we can write this as hydronium times 0.9 molar divided by 1.1 molar. That is going to equal 1.8 times 10 to the minus 5. So if we want to know what the hydronium concentration is, H3O plus, it would be 1.8 times 10 to the minus 5. I'll put this in parentheses over here, times 1.10 molar over 0.90 molar. Okay, so let's see what that works out to be. Let's see if this nifty calculator can do it. 1.8 times 10 to the minus 5 times 1.1 divided by 0.90. And you get 2.2 times 10 to the minus 5. So now let's calculate the pH here. Let me make a little more room. pH would be the negative log of 2.2 times 10 to the minus 5. Okay, well, I think we have that number still in our calculator. There it is. So let's just take the negative log of it. 4.66. And there's our pH. So what's happened? Before the reaction took place, before we added the HCl, the pH was 4.74. And then the final pH was 4.66. That's not a very big difference, right? That's a difference of negative 0.08 units. Remember, pH is unitless, so I'll just call it units. It went down. It became more acidic, but not by very much. Only 0.08 units. That's a pretty small difference. Let me compare that to what would happen if we did the same thing with water. Suppose we dissolved 0.1 moles of HCl into 1 liter of water, pure water. Now, pure water is pH 7 in theory. It usually isn't, but in theory it is. So the question then is, if you start off with water at pH 7 and then you add 0.10 moles of HCl, well, the question is how much? It's a liter. So this is a strong acid, so 0.1 moles divided by 1 liter is 0.1 molar. Back in chapter 16, we learned that if you want to calculate the pH of a strong acid, all you need is the concentration of the acid that you're dissolving. So the pH would be the negative log of 0.10, which is 1. So what's happened is, if this were pure water, adding 0.10 moles of HCl would change the pH from 7, neutral, all the way to 1, extremely acidic. However, if we use a buffer solution using sodium acetate and acetic acid, the pH would go from 4.74 just down to 4.66, a very small difference. Okay? So that's the significance of buffers in a nutshell. Now, I didn't show you here, but it also goes for bases. If you add a strong base to a buffer, it also resists changes in pH. In that case, what happens is the strong base reacts with the acetic acid. Now, I want to show you a couple of important quantities that you'll use in this, really for the next couple of sections, and that is the concept of pKa. It's important. pKa is defined as the negative log of the Ka. So, for example, let's say we have acetic acid, and it has a Ka of 1.8 times 10 to the minus 5. The pKa would be the negative log of 1.8 times 10 to the minus 5. Plug that into your calculator and you'll get 4.74. So it's a way of representing the Ka, but as a logarithmic function. Suppose we have HF, and it has a Ka of 7.1 times 10 to the minus 4. The pKa of that particular acid would be the negative log of 7.1 times 10 to the negative 4, which comes out to 3.15. These are numbers I've seen quite a bit. So your textbook does have a nice table, actually in this section where it shows you the different values of the weak acids, the Kas and the pKas. So HF, for example, has a pKa of 315. Nitrous acid, HNO2, has a pKa of 3.35. Formic acid has a pKa of 3.77. Benzoic acid has a pKa of 4.19. Acetic acid, 4.74. Hydrocyanic acid, 9.31. And then phenol, very, very weak acid, 9.89. Okay, so pKa values are useful. What happens is the larger the pKa becomes, the weaker the acid is. So this is in the direction of weaker acid. So in this list, this would be the strongest. And there are stronger weak acids in HF, but that's one in this list. And then this would be the weakest acid in this list. Okay. Again, strongest not meaning it's a strong acid. It's not HCl or HBr or HI, but it's the strongest in this small, very short list of weak acids. The other thing I want to show you is an important aspect of buffer calculations. We could have used it in the previous problem that I showed you, but in keeping with the textbook, I didn't. And that is something called the Henderson-Hasselbalch equation. I guess we could abbreviate it, right? HH equation. Looks like hydrogen. It's a Lewis structure for hydrogen. Henderson-Hasselbalch equation. It's based on the idea of Ka, the definition of Ka. So for a generic acid, the Ka is the concentration of hydronium times the conjugate base concentration divided by the concentration of the weak acid. The Henderson-Hasselbalch equation is a nifty logarithmic equation. So what you do is you take the log of both sides, so you get the log of Ka equals the log of this whole mess here, right? Concentration of hydronium, concentration of the conjugate base over concentration of the weak acid, right? Then what you can do is you can separate out the conjugate base and the weak acid from the hydronium concentration. The log of the products of two quantities is equal to the sum of the logs. So this would become the log of the hydronium plus the log of the ratio of the conjugate base over the weak acid. And you could, if you think about it, you could separate the second term out into two terms, log of A minus minus log of HA, but we don't do that with the Henderson-Hasselbalch. So that's equal to the log of Ka. The next step is to multiply everything through the entire equation by -1. So you get negative log of Ka equals negative log of the hydronium concentration minus the log, again, of that ratio, the concentration of the conjugate base over the concentration of the weak acid. Okay? So then start thinking about it. Negative log of Ka, we already defined that just recently, that's the pKa. And the negative log of the hydronium, hey, that's the pH minus the log of this ratio. Okay, and then just to clean it up a little bit, typically pH is on one side and everything else is on the other side. So we add the log of the A minus to HA, and you get pKa plus the log of this ratio is equal to pH. And that's the Henderson-Hasselbalch equation. That's the general form that people normally quote. The pH of a buffer solution. This is used with buffers. If you have a reasonably high concentration of a weak acid and its conjugate base, so for example, acetic acid and acetate, or hydrofluoric acid and fluoride, the pH of that buffer is equal to the pKa of the weak acid, 4.74 for acetic acid, 3.15 for hydrofluoric acid, plus the log of the ratio of the concentration of the conjugate base, that would be acetate concentration, divided by the concentration of the weak acid, acetic acid. Okay, so if we were going to do this for acetic acid, it would be 4.74 plus the log of the ratio of the concentration of the acetate divided by the concentration of the acetic acid. That would be equal to the pH. And there you go. So this is the Henderson-Hasselbalch equation. You'll see it in some of the problems.